So we'll start lecture 10 today. So I added a couple of new references to our list of references, especially for convolutional neural nets. So if you want to go and study a little bit more in detail, recommend the reference number 3. There's also reference number 4 that I'll be using material from for this lecture as well. So feel free to take a look at that. Okay, so today it's just very simple. We'll just go through convolutional neural nets, or CNN for short. So convolutional neural nets, you'll see something that looks typically like this. There's like an input and it's almost always an image. And then you'll see like, volumes or kind of boxes that keep getting transformed from one to the other, right? All the way to the output. So this is one example. And you can say, well, in the beginning, you're doing some feature learning, and at the very end, you're doing classification. So your goal is classification, but the raw image does not have, the features already extracted that you can right away do the classification. So if you remember from our earlier lecture, maybe our first or second or third lecture, we did convolutions, and we looked at different kinds of convolutions on images. We looked at the blurring convolution, we looked at the smoothing convolution, we looked at the edge detector, right? So all these convolutions, apparently do matter a lot as far as classification is concerned. So we don't have to reinvent the wheel in terms of what is good for images, what kind of features is good for images. Convolutions are apparently very good. The only thing is, instead of you and me deciding what convolution to use, let the deep learning model decide what convolution to use. So that's the difference right now with the convolution neural nets, right? Okay, and there's a few other things here. We'll talk about it as well. Here's another example. So you have an input image. This is a kind of a functionality breakdown. So functionality breakdown is like, the first functionality of the CNN is to do feature extraction. And it kind of does more and more refined feature extraction. It starts with coarse grained features and goes more refined as you go through the layers. And then the second functionality is classification. So you see, this is familiar, right? This is familiar from like a feed-forward neural network. Right, so we looked at this kind of an architecture before, and that's where and we also said these are like dense features, right? And then the last one is just a probability distribution. So for classification, you almost always want to output a probability distribution across your different classes. So here's an image of a cartoon character, and then you say it's a Donald, or it's a Goofy, or it's a Tweety with some probability, right? So in this case, you see Tweety has a high probability. That makes sense. So functionally, this is what is happening in a convolutional neural net, is most of the work isn't just extracting features. And we know this even for machine learning in general, that most of the work, 70% of machine learning is extracting good features or feature engineering. So even for a neural net, it's like spending 70% of the effort in just getting good features layer by layer. And then once you have the good features right here, this particular layer is like the golden layer where all the work has been done to extract important features that the neural network thinks is important based on the data, and then uses it to do the classification at the very end, right? So that's a functional breakdown for neural net. This is another one, very similar. Nothing really different. We only change the image from a cartoon character to an animal. And again, the output is a probability distribution over the classes. So here, the probability distribution, I should mention, softmax, is basically e to the negative zi over summation e to the negative zj, let's say. So this is the probability for the ith class is e to the negative zi over that. And what is z? Z is coming from the previous layer. This is z. So you take each of these z's and then make it into a probability distribution. So that's the final layer of this CNN, is to take whatever you output from the fully connected layers and convert it into a probability. And how do you convert? It's using softmax. So you just need, like, let's say you have k classes here. Just need k floats here. It doesn't matter what those floats are. The CNN knows that you will convert it into a probability and then you will output a result. So it will use that to train the loss function accordingly, right? So you take these k floats and convert into k probabilities, and then use these probabilities to make a prediction. So hopefully you pick the class that has the highest probability as the class that matters, right? In this case, it's zebra. So hopefully you assign the highest probability to zebra. Then you're doing a good job with the CNN. All right, let's look at it in terms of layers. So you can see that there's many different things going on, at least a few different things going on. So there's the input layer, and then there is, between two layers, there's something going on. So here you can say there's a convolution that's happening, and there is a max pooling, and that's happening. There's a convolution that's happening again, and there's a max pooling that's happening again, and then there's a fully connected layer that's happening. So there's a full connection between two activations. This is one activation, this is the other activation. There's another fully connected thing, and then you might have, okay, see, there's a dropout here as well. So we spoke about dropouts some time back. So you can insert dropout, just like you inserted dropouts in neural networks to avoid overfitting. You can now insert dropouts in the last layers, fully connected layers, to again avoid overfitting and make sure that you have a good model. And then you'll have a softmax, and you'll generate a probability over different classes. So in terms of layers, something new that we are seeing is convolution layers, and then max pooling. So these are something new and unique to convolutional neural nets that we don't find in a regular neural network architecture, right? Another example of layers breakdown. So let's say you have a picture of a bird and you're doing feature extraction here, right? We spoke about functionally what's happening. Functionally, you're extracting good features. So here, essentially, the feature extraction is happening through a combination of convolution and pooling. Convolution pooling. So this is how it's working. And it might be, a couple of layers, it might be 10 layers, depends on the data that you have, depends on the complexity of your task. Sometimes you want to go from, there's something called universal image encoding. So it doesn't matter what image you have, you want to encode it in a way that your downstream task, so we call this a downstream task. The idea is that, you in many of these image classification problems, you may want to use an encoding that's kind of universal, or you want to train on massive images like AlexNet or one of these nets that we have publicly available. They train on millions and millions of images so that they can generate these features that can support many different downstream tasks, right? So this part is super critical, like this feature extraction part is super critical. And in those kinds of networks, you will see that it's like very big. It's like 10 layers or 15 layers before they even start doing something. That is because you want it to be a universal encoder. You want it to apply to many different kinds of images. Then you need such a powerful network. So depending on your task, you may have a few layers or many layers, or you might use a pre-existing net that's already available and then fine tune the last few layers for your data set, and then use the features coming out of that for classification. So again, the idea is someone has done a lot of work. There's no need to reinvent the wheel. You can start from where they left off and fine tune the last few layers, and then use that with your downstream task. So this portion is your downstream task. So only work on this part. Don't reinvent the first part. Maybe fine tune it a little bit. So that's called a pre-trained model. So when you already have a model that someone has put in a lot of days or weeks worth of effort, just fine tune it. That's something that you call a pre-trained model. So you'll encoder this already trained, but can fine tune last few layers. So a lot of people do use pre-trained models in computer vision and natural language processing because, yeah, why would you want to reinvent the wheel? But hey, it's still important to fine tune those last layers because your task might be different. So this pre-trained model is generic. It applies to many different tasks, maybe classification, maybe captioning images, maybe detecting object detection. People have thought about different tasks and they said, okay, here's a nice pre-trained model. But you need to fine tune for your own task, and then you can make a prediction using the last fully connected layers that you have here, and then make a prediction for your specific task. So that's typically how people kind of break it down. Feature extraction is the first half, and then your downstream task specific architecture is the second half. So a lot of times you look at any kind of architecture for any task, the first half is typically similar because it's feature extraction. So that okay, so whatever it is, I'm dealing with an image, I need to extract features. It's going to be kind of similar. At least that's what we've been seeing for most of the models. Okay, so how does neural network compare against convolutional neural network, right? So let's just kind of look at it. This is a neural network and this is convolutional neural network. So let's say feed forward. So you'll hear feed forward, you'll also hear FC, which is fully connected. So this is FC, right? This is FC because every neuron here is connected to every neuron in the previous layer. So it's fully connected. There's no breaks in any connection. That's why it's a FC. You also call it dense because it's dense. There is no breaks. It's not sparse. So you'll hear sparse or dense. Dense means it's like mostly fully connected. Doesn't have to be fully connected, but it's like there's enough connections in there. Sparse is like, there's a lot of breaks. There's a lot of connections that are missing. So that's sparse. So FC and dense are synonymous. Okay, so what's the difference between neural network and a CNN? In neural network, your hidden layers are vectors mostly, right? Also, you can call it neurons. And then between two layers, you have dense connections, right? Between this layer, input layer, and the hidden layer 1, you have dense connections. Between hidden layer 1 and hidden layer 2, you have dense connections. And then you have the output layer. So when you move to CNN, you see that instead of a vector, you have a block, a volume, or more appropriately, you have a tensor, right? So actually, you have a tensor for your neurons, and then you have a transformation that happens on these tensors, and then you get a different tensor. So here we are moving from a vector to a vector, right? In neural networks, one vector, second vector. Maybe here you say, okay, this is phi 12 dimensional, and this is maybe phi 12 dimensional. This is something else. Maybe this is 1000 dimensional, and then this is obviously one dimensional or whatever, how many dimensions here. But here you're typically starting with your input is actually an image. So image, you see there is like this small depth here. That's for RGB, right? So this is your width, this is your height, and then this is your depth. So when you talk about a volume or a block or a tensor, you want to see it that this is the width, this is the height, and what you see right in front of you, that's the depth. And for the input, it's obvious the depth is RGB. So you have RGB, so 3 different depth slices. So you can call it slices. So you have 3 different depth slices. But for the hidden layers, you can have multiple depth slices. So instead of 3, you can even have 10. And we'll talk about what that 10 means. And then they can transform this way, and then finally you get something at the very end. So you're looking at something that looks like W by H by D. So a block, width, height, and depth, right? Your final output, typically is 1 by 1 by K, where K is number of classes. Because no matter what your input is, what your hidden layers are, what your volumes in between are, at the very end, what are you doing? You're making a prediction. And that's going to be like K different vectors, K different values that are probabilities, right? So why do you need any of the other dimensions? Those are going to be 1, 1, and then you're going to have K, right? So even though you see a volume that looks like this is actually 1 by 1 by K, okay? So one other thing I want to mention is, even though we're looking at vectors here, the transformation between two vectors in fully connected layers, that's a matrix, right? This is a weight matrix. We've spoken about it, W1, W2, and so on. So between two layers, how you go or how you transform, that's using a matrix. But the layer itself is a vector in neural networks. In CNNs, the layers themselves are tensors or 3-dimensional. You can say it's a 3-dimensional vector or 3-dimensional matrix, however you want to call it. So you get a block. And then the transformation between these two layers, that's something we're going to talk about. So those are kind of, there's more involved when you want to transform a CNN block to another CNN block, right? Or you want to go between these layers. There's like different things you can do. Does it make sense so far? Yeah. All right, so a little bit more description on CNN versus NN. So CNN is obviously a special type of NN, right? It's a neural network. Everything's all the neurons are getting connected in specific ways. So it's still a neural network, but it's a special kind. So we call it CNN, Convolutional Neural Network. And it's specialized images. This is key. So you see the input here is an image. The input here can be anything in a neural network. So almost always a CNN takes in an image. So that's why when people start working on images some time back, they realized CNN works well, and then they stopped using any other architecture. They're like, hey, yeah, sure, neural networks are great, but for images, I'm not going to do anything other than CNN. So almost every paper that got published after 2012 has been using CNN for images. People are like, yeah, we can mess around in the CNN space. There's a lot of things to mess around, but let's not go outside because we know it doesn't work so well. Okay, specialized images. So fully connected layers, like we saw in neural networks, yield too many parameters weights, right? It's fully connected. If you go from 1,000 dimension to 1,000 dimension, that's like 1,000,000 parameters in between because it's fully connected. Every neuron in the output layer is connected to 1,000 neurons in the input. And there's 1,000 neurons in the output. So that's 1,000 times 1,000, which is 1,000,000. So you see very quickly things start scaling up. And that's just for a vector. Now, if you think of an image is actually a matrix. So it's like 2 dimensions. So you have to multiply the 2 dimensions to actually, put it into a vector format. So as soon as you increase the resolution, we already saw, if it's a 100 by 100, you have 10,000 here. If it's 1,000 by 1,000, you get 1,000,000. So even the vector itself is 1,000,000 dimensional. And then the parameters are, multiplying that dimension with this dimension. So the parameters just go up really crazy in a fully connected neural network. So FCs lead too many parameters. So that's a drawback of using neural network anyway. It's not like the most scalable way to do machine learning for images, because things just blow up. Also, more intuitive feature engineering, like we spoke about it. Convolutions is an important feature or important transformation that happens in CNNs, but the convolutions themselves are picked by the CNN. So you just say use this sized convolution, but CNN says, okay, I think I'll use this convolution. I will learn it from the data. So you let it decide what it wants to learn, but you put in that structure and say you have to do a convolution, right? So more intuitive feature engineering is done by CNN as compared to a regular neural network, because it's working with the convolutional structure, whereas neural network has no concept of convolution. Like where is convolution happening? It's just doing dot products, right? Matrix vector multiplies. So there is no specific convolution structure that shows up in a neural network. Okay. And CNN works on a block with a height, width, and depth, like we spoke about. Whereas in neural networks, the layers are encoded as vectors. Okay. All right. So let's look at the type of layers or transformations that you can have in CNN. So the first type of layer is a fully connected layer. You can still have a fully connected layer in CNN, although it has a specific purpose. Like we saw, it shows up usually at the end of CNN. So usually you use it at the end. You don't use it at the beginning. And we'll see why. I mean, we'll see a little bit more intuition behind why FC is used in the end and not in the beginning. Okay, so that's a FC. So you can still use FCs in CNN, right? And then, but the new things, the new kind of layers or transformations that happen in CNN is a conv layer. So conv layer is something that is kind of the most important and the most frequently used layer in a CNN architecture. Here, one or more, so this is the key, one or more, typically more, it's not usually not one. You might have like 5 or 10, like it's usually not one. Convolutional kernels are learned as parameters in training. So like imagine you have, this is one convolution. Let's say this is 5 by 5. Remember you had those 5 by 5 or 3 by 3 convolutional kernels, and they had specific values to do blurring or edge detection on images. So that is something that our CNN is going to learn, and you're like, okay, this is not enough. Let's have one more. Let's have one more. Let's have one more, and so on, right? So maybe you have 10 of these, and each of these are different, right? They might learn different aspects. They might learn different things from the image. So every convolution learns something different, right? As we saw, a convolution can be used for blurring or edge detection or denoising or whatever. So they can do different things and learn different things about the same image, about the same area of the image. You can learn different things. So you say, okay, I think I'll use 10. That's a hyperparameter. You decide how many you want to have, and you transform one layer to the other. You can have 10 or 15 or whatever. That's up to you. That's a hyperparameter that shows up in CNN. And then each of these gets convolved with the input, and you get another input. So when you convolve a kernel with an input image, you get an output image that has similar dimensions, right? So you know that. We know that. The only thing is, instead of having just one image, you're going to have 10 such images, which again becomes a volume, right? Like what's a volume? It's just images stacked together in our scenario, right? Does that make sense? If you think of this as an image, these are also like you can say hidden images in some sense, hidden layer images, because each of these is one image, right? I can visualize it. It's coming from an image. It may or may not make sense, but you can still visualize it. So the beautiful thing about convolutional neural networks is you can visualize the intermediate layers. Whereas in neural networks, you just get some floats, and you're like, what do I do with these floats? I may not be able to interpret it or understand it as well as in CNNs. So CNNs give you some more ability to understand what's happening in the intermediate layers. Just visualize it. You can just visualize and know what exactly these features are that are being learned through these convolutions. So the way to think about this block, if this block is of size, the depth k, there are k latent images that are being learned, right? And then you go to the next block, you have a different depth. Those many images are being learned and you just stack it together, right? So you're going to convolve each of these kernels and produce an output block with the same depth as the number of convolutional kernels. So if you choose k equals 10 here, you're going to get a output block of depth 10. Or if it's 15, you get depth 15. So depends on how you're setting it up. It doesn't matter what the input block size was or depth was. Maybe you start with an image, RGB image, that's a depth of 3, right? But your hidden layer, you can say, I want to use 10. So you use 10. So we'll look specifically into how the convolution layer works. So even though you have a depth of 3 here, you can produce a depth of 15. So how does that happen? We'll kind of look into the mechanics of that. And then there's the pooling layer. So pooling layer is again new, something new that we don't see in neural networks. So what does pooling layer do? It's very intuitive. It's what it says. It's pooling things. It's pooling information. It's saying, okay, maybe there are 4 pixels here. Can I compress it to 1? Like, do you remember we did averaging through while sliding through? I think we did pooling as well. We looked at pooling as well. When you change the stride length, you can look at adjacent pixels or adjacent blocks of pixels and not have overlap. That's exactly what pooling is. Pooling is just kind of sliding the window, but not having overlap between 2 slides. And so you just like go here, 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 here. So you're just kind of going through the image, but not having overlaps, and then collapsing that into 1 pixel value. So how do you collapse? There's different ways of doing it. You can collapse using averaging, or you can collapse using max, taking the max of the pixel values. So again, people have done experiments on this, and they've figured out that max pooling works the best as compared to averaging. So you'll see that most of the neural nets that use pooling will use max pooling. Well, these days they're also trying to not use pooling. That's a different story. We'll talk about it later. And then there's ReLU activation. So ReLU activation, we looked at same thing as a neural network architecture. You take a set of neurons, you pass in through a nonlinear activation function ReLU. If it's negative, set it to 0. If it's positive, let it pass. Or if you have leaky ReLU, you have some kind of leaks. I'm just going to close the door here. Yeah. So ReLU activation function, if you have, if you can use a ReLU or a leaky ReLU. So again, to refresh our understanding, a ReLU looks like this. So rectified linear units, right? So it's a linear unit, rectified. This is linear unit. So it's rectified because it's not linear. You've kind of adjusted it for your purpose. So that's why it's called rectified. And even though it says rectified linear unit, it's not a linear function. We spoke about this as well, right? This is a combination of 2 linear functions, which is not linear. It's a nonlinear activation, nonlinear transformation. So you can use ReLU activation just like in neural networks. So the new thing in CNN, in terms of the layers, is a pooling layer and the FC layer, Conv layer. These are the 2 new kinds of layers that we use in CNN. Okay. So let's understand it in terms of a neural perspective as well. I don't think we spoke about it in specific ways, but in our brain, we have these neurons, and a neuron take input from other neurons, and these inputs are called dendrites. It's like, this electrical signals or impulses happening. So you can actually look it up in biology. It's called dendrites. So the dendrites come into this is a neural cell. That's what we call a neuron. And then this neural cell is basically aggregating information. It's doing a dot product and summing it up. So what you think is a mathematical operation is actually happening in your brain right now, right? As you're hearing me, as I'm speaking, There's some neurons that are kind of, going to different cells, I mean, millions of cells, and then aggregating the information, doing a dot product, summing it up, and then passing it out. So this passing it out, it's called an axon, dendrite axon. So you can think of what's happening here from that perspective as well. The only thing that's different in terms of taking a dot product is we're taking local dot products, because when you look at the conv layer, and we'll talk about it, you're actually sliding across the image. So this dot product is happening between the convolutional kernel and just this part of the image, not the whole image. Whereas in a fully connected layer, you're taking a dot product with all of the neurons in the pass layer, right? So if you remember a fully connected layer, and if I want to compute this, I actually have to take a dot product with every single neuron in the previous layer. But here, this is the previous layer, but I only compute the dot product in this region for this neuron. So this is a local connection. Then I might move on to something else. I might have another neuron sitting here, and that's going to pick up something in this region. So this is called local connectivity. So CNNs have local connectivity, which neural networks don't, right? Because neural networks, and especially if it's a FC are fully connected, but you can say this is, so this is like locally connected. Okay. So still taking, so if you think about convolutions, right? If you want to look at the output of a convolution, you say, how did you get that output for any given pixel in that output image? It's a dot product. Do you agree? It's a dot product between the convolution and the specific part of the image that you took a convolution on. So, but it's a local dot product. So that's why we say locally connected. So the nice thing about convolutions is we are still working with dot products. The only thing is it's localized instead of using all of the layers. So that's the difference. Okay, so this analogy still applies of taking in inputs, multiplying it with weights, summing it up, and then doing something with it, right? Activation function, maybe ReLU, and then passing it on. So this analogy still applies to CNN, just make it local, like look at specifically what neuron you're looking at, and then use the appropriate input region for computing it. Okay. So let's look at the convolution layer. This is a little bit, there's a lot of details here to understand. So let's look at it one by one. So what are the parameters in the convolution layer? So like we said, convolution kernel is operating on, let's say this is our input image. Okay, so this is my input block. It has a depth D. Doesn't have to be 3. Let's say you're in the intermediate layer, it can be 10, can be something else. This is your width, this is your height. Yeah. So the interesting thing is the convolution kernel is going to have the same depth as the input here. So this is going to be W, H, and D, but it's going to be smaller, right? This might be 3, 3, and then this is D. Because for any given, let's look at the output. So maybe output looks like this. Maybe this is W2, H2, and maybe this is different. You have a more depth in the output. Maybe this is D2. Doesn't have to be the same depth as the input block, right? This is the output block. So how do you go from here to here? Because of this convolution. So what you're going to do is, if I want to understand how did I obtain this particular neuron here, well, this neuron actually has a depth. Okay, Okay, let's say this specific neuron in this depth slice, let's say in the first depth slice, how do I obtain here? So then I'm going to look at this region here, and it has a depth. I'm going to take all of the depth. So all of the depth gets used in the convolution because this convolution also has a depth. So you take this block and do a convolution. So that's a dot product. And then you get single value, and that single value shows up here. But this is for every single depth here. So you're going to have many such, so this is again D. So this may be, let's say this is convolution 1, this might be convolution 2, and so on. So you have like D2 such convolution blocks that are convolving with the same region, right? I convolve with the same region and I get a vector here, this vector. So you look at each of the depth slice, it's coming from one of these convolutions. Maybe this one is coming from here. Sorry, this one's coming from here. And then maybe you have something else here, sitting right here. That is coming from this guy. And then maybe you have something else here. And that's coming from maybe another convolution. And it has the same depth, but it looks different. Like it can be anything else. So you have D2 such convolution blocks that are convolving with the depth, with a block in the input block, and then producing your output that looks like this. And then you do that for every single pixel value. Right? Just keep sliding these convolution blocks. Okay, so does that make sense? So the convolution now has a third dimension as well. Whereas in your convolution that we looked at in our initial lectures, it only had an image, right? Now we have a depth because the input also has a depth. So this convolution is ready to handle color images or images with depth. Okay. So the depth gets factored out. So this D is not showing up here. This D2 is because of these different convolution kernels. The depth D here gets factored out because you just take a dot product and you get a single value, right? You're not getting a vector. The vector is coming because of the different convolution kernels that you're using to convolve with the same part of the image. Like you're using this convolution with this with this, and this with this, right? So this implies that if you have k such kernels, then the output block has a depth of k. So the k that you see, the depth that you see here directly corresponds to the number of kernels that you have used in the convolution layer. Okay. So again, I just want to differentiate. There are two different depths that you use here. The first depth is the depth of the convolution itself, which is the depth of the input layer. So that's not going to be different. So even though you have WHD here, you have 3x3 convolution, the depth itself is going to match the depth of the input. So that's for the convolution. But then the output depth depends on the number of convolutions that you use. So two different depths that are happening in this image here. Okay. So that's the parameters. Parameters are just the parameters corresponding to each of these convolutions. So if I have k convolutions, I have, let me use a different color. Yeah, so if I have k convolutions, I have k by W by H by D. So this is one convolution block, and this is k such convolutions. So each convolution block has W by H by D parameters, you agree? Because that's the convolution block. And I have k such convolution blocks. So the number of parameters in just going from one layer to the other is k times W times H times D. Just from one layer to the other. And then you have many such layers. So you have to multiply all of those to get the total number of parameters. And we'll see that this is not as much as you think it is as compared to a FC layer. It's much, much less than you might. So there is like a lot of advantages or wins that you get by using a convolution layer as compared to a FC layer. Hyperparameters. So we spoke about parameters. Hyperparameters, as you can imagine, is K. Like we said, how many of these are you going to use? 3, 5, 10. Okay, so that's K. The number of convolutional filters or kernels that you're going to use to convolve with the input block. Then there is something called stride length. I think we spoke about this briefly, but we'll also look at it. How do you shift your convolutional kernel as you pass through the input image block? Are you going to shift one at a time? Are you going to shift two? Are you going to shift by a lot? That's the stride length. And then zero padding P. So how much zeros do you want to pad? How many layers of zeros do you want to pad around the input? And this impacts the output size. So you can pad in such a way that the input to output size is always the same. So input size is the same as output size. So you always get the image of the same dimension. You can pad and you can decide the padding so that you get that result. So these are hyperparameters that you have to play around with, right? K, S, and P, I cannot put that as parameters. It's obvious. Like I can't do gradient descent on these guys, but I can do gradient descent on the floats sitting inside the convolution kernels. Okay. So we call F to be the receptive field size of a convolution kernel. So this typically it's F by F. So this is the receptive field size of a convolution kernel. It's called receptive field size because that's the receptive area that you're going to handle in an input block. I'm only receptive to that. That's also, you can say it's local. It's only local to that size. So fancy names, but means what you think it is. It's just like local to that input block. So that's the reception area. So receptive field size is F. S is a stride length. So we'll look into how to visualize a stride length. P is the zero padding. If this is true, if you have F, S, and P, then you can determine what the width of the output block is going to look like based on this. And it's a formula that's like W minus F plus 2P over S plus 1. Okay, how do you know this is true? You can check that this is true, but let's say S is equal to 1. So that means you're sliding the convolution block one at a time. Then you know that you'll lose F, right? As you slide, because the size of the convolution is F by F. So you're not going to be able to go all of the width. You're going to stop F before the width. So that W minus F makes sense. Let's say there was no zero padding. So this P is 0, S is 1, then you get W minus F plus 1. So if S is 1, P is 0, and you have an F, this implies output width is W minus F plus 1. Does this make sense? Intuitive? Yeah. So now if you have an S, then what happens is you're striding by 2, you're skipping by 2. So you're skipping every 2 pixels, then you're going to divide by 2, right? Because your width has shrunk by 2 because you keep skipping every 2 pixels. So that's why you divide by S. Okay, that makes sense. Padding, well, you add the padding because padding just adds to the output size. So it turns out P is just, you add a padding around the image. So you add on both sides. So that's why 2 times P. So if you only add on one side, it's P. So now you have 2 times P. So that's why it's plus 2P. So this, now it makes sense. W minus F plus 2P over S plus 1 will be the width of the, so basically if you have D, so this width of the output block is going to be W of the input block minus F plus 2P over S plus 1. So from going from input to the output, how does the width change? You can pick a P, a padding in such a way, or an S in such a way that this whole quantity is the same as W that you had in the input as well. So the input and output blocks have the same dimensions. People sometimes do that when they do CNN training. They don't want to lose information, or they want it to look similar. You can have it that way. So this is an important formula to remember for CNN. And it's not something you have to memorize. You can just intuitively understand how you come up with this, right? Um, okay, we spoke about stride. So 3 hyperparameters, K, this makes sense. Zero padding we looked at, I mean, we can look at it again. It makes sense. So let's look at stride length S. So to understand strides, let's just understand in one dimension, right? So here, let's say you have a 1D input. So notice we have zero padding here. So what is P here? Anyone? Just based on what you see in the input. So remember, this is one dimensional. If it was an image, you would just add one whole layer around the image, right? And that would be P equals 1. Here, it's a vector, so the same idea. So P is still equal to 1, but you add on both sides. That makes sense? So P is equal to 1. So here, if you want to get the output here, let's look at the output value here. That's coming from this, this, and this. So what is your F? The field size here, the reception size. You can just type in the chat. 3, yeah. Because you're only looking at 3 pixels or 3 input values in the input. So that's your reception size. So F is 3, P is 1, that makes sense. And there is a striding that's happening here, right? You're moving from one set of 3 pixels to the next set of 3 pixels. So what do you think S is in this case? Again, you can type in the chat. S is 1, yeah. So you're shifting only by 1. So if I go from this green to the next one, it looks like this. So I shifted by 1 here. So whenever I go from one to the other, and then here again, I've shifted by 1. So when I look at this, again, I shifted by 1. So that is the stride length. So how much are you shifting from one set of local inputs to the next, right? What about here? So P here is still the same. You agree? In this example, P is 1. F, still the same. What is S? Type in the chat. 2, yeah. Because look at, you start here and then you're able to go until here. So your F is 3, that makes sense. Your field size is 3. But when I move my convolution, I'm shifting by 2. So S is 2. Again, when I move, I shift by 2. So this is how you know S is 2 in this example. Okay. And because you've changed your S, like we spoke about, if you make S equals 2, you're going to divide by, it's going to reduce roughly by half. So you see here you have 5 as your output size, but here you only have 3. Because the higher your stride length, the shorter your output size. Yeah, because you're dividing by S. Yeah. Okay. So why does stride length matter? Well, usually people keep stride length to be small. They don't want to lose information. Because if you skip too much, if you keep S equals 5 or whatever higher number, what are you doing? You're just basically skipping a lot of information. So as only for the sake of maybe reducing the number of parameters, you may want to increase the stride length, because as you can see, the parameters went by half when you kept S equals 2. So that's a reason to reduce the number of parameters. Maybe you think there's overfitting happening, but as much as you can, you want to preserve information. You don't want to have a very high S. So a low S is typically what's used in practice as a hyperparameter. Okay, So now we get to the important aspect that we really need to understand here is how does a convolution actually happen uh, when you go from an input block to an output block. So this figure has a lot of information. So let's kind of parse it. Let's look at the input here. What's the input size? Well, it's right here, 7 by 7 by 3. And it's 7 by 7 by 3 because P is equal to 1, right? So here you see P is 1, you kind of pad it all around with zeros, but you're only padding it 1 in one layer. So that's why P equals 1. What is F in this case? Type in the chat. F is 3, yeah. And let's assume S is equal to 1. What is the input depth? Three, yeah. What is the output depth? Yeah, it should be obvious too, right? It's 2. So you can see your output. This is the output block, right? 3 by 3 by 2. So that makes sense. Okay, so what's happening here is each of these is a depth slice of the input, right? The input has a depth 3, so you can slice it into 3 different images. So you see this is the first image, second image, and third image. So it's indexed here, 0, 1, and 2. These are the three slices. And then we're not just happy with the slices, we also pad it with zeros. So you see padding is there. And these are your filters. This is the first filter that's learned and the second filter that's learned by your CNN. Okay. And each of these filters also have a depth, and the depth is the same depth as the input depth. So filter 1 has a depth 3. So those are the 3 depth slices of the filter 1 or convolution 1. And then convolution 2 also has a depth of 3, and then these are the 3 slices. And because f is equal to 3, you see these are 3 by 3. So you have a 3 by 3 convolution kernel with a depth 3, and you have 2 such convolution kernels because that's your D2. Your D2 is 2, so you have chosen 2 such convolution kernels. And then you use these to convolve to get the output volume. Okay, let's look at how this convolution works. So let's say I want to look at this particular entry. This is in the first depth slice of the output volume. Yeah, that makes sense because we're looking at the first depth slice and there's the second depth slice. So because you're looking at the first depth slice, you need to use the first convolution filter to convolve with the inputs and then get this value. So like we spoke about, the convolution is happening across the depth as well. It's not just convolution over the image, it's also across the depth. So you're basically going to take a dot product with all the values, sum it up, and then you get the output. So let's take a look here. I'm going to convolve this with this because that's the first entry here. So I'm going to look at this block. Does it make sense? And for this depth slice, I'm going to look at this block. And for this depth slice, I'm going to look at this block. So you can see in all of these, the non-zero portions are here. So I only need to look at this portion. So that's going to give me, this is going to give me 2, 1, 3, 4. Yeah. So I'm getting 4 here. When I take a dot product, if I look at this, what do I get? So again, the non-zeros are in this region. I'm how to take a dot product with this kernel. You can just type in the chat. So you can ignore all the other values here because these are zeros. Only look at the 4 by 4 block here. and take a dot product with the corresponding kernel here. So you get 0, okay. And would you say the same thing for this one? Yeah, because you're 1, -1. So you get 0 as well. So I'm going to sum them up because your convolution is happening across a depth. So I get 4, but hey, the value here is 5. Why is that? Because there's a bias term as well. So 4 plus 1 gives me 5. So to get the output value here in the first cell, I am actually taking this convolutional kernel and convolving it across the depth with the input, and I'm getting that value. So I'm going to do that for every single pixel value here. So if I want to look at 8, the same thing. Now I have, I think here, okay, so just looking at this and this, what is the stride length? So you see that you started here we are starting here. So stride length is 2. Okay, so I didn't know what the stride length is, but just looking at how we went from one to the other, it's obvious that S is equal to 2. So S is equal to 2 is what's being used here. And you do the exact same thing. You get some value here, sum it up with this, sum it up with this, and add the bias, and that gives you 8. So we're going to do this across. So essentially, we're taking local dot products between the convolution kernel and the input block, and we keep striding along with the stride length, and then you get the output block. And you have to do the same thing for the second depth slice of the output block by using the second filter. So we repeat the same process with the second filter, and you get the second depth slice. If you had 10 filters, you'd have to repeat it 10 times with 10 different filters, you get 10 different sets of output slices. And you put that together, that's your output block. Okay. So your output volume is obviously, you can decide the width and depth based on the formula we spoke earlier. Because we're using a stride length of 2, you can see that the width and the depth height have reduced by a factor of 2, which makes sense. If you didn't, then it wouldn't reduce so much. And the output depth is 2 because you're using 2 filters. So it doesn't matter what the input depth is, the output depth is just based on the number of filters, number of kernels that you're using to convolve. And hopefully these kernels are capturing different pieces of information, and you're learning something new every time you use a filter. And you stack it together and pass it to the next layer. The next layer learns something else, and then the next layer learns something else. And finally, at the very end, you say, okay, I think I have all the information I need from this image. Now let's do classification. And then the CNN switches into classification mode. It uses fully connected layers, has dense connections like we've seen earlier, and does a classification. Okay. All right. Any questions so far? Okay. If not, let's just take a 5-minute break. We'll come back and then we'll go through more convolution stuff. Okay. So actually we have an in-class exercise, but before that I want to show you an animation here. I've shared the link to this in the, what's happening? So I shared a link to this in the reference to the PDF as well. So kind of go through this animation here. So this is showing essentially how you can convolve two convolution filters with an input volume to get an output volume, right? So we saw a couple of examples of this, but let's just look at it as an animation. So you can see on the right, the output is moving through the output volume, and then how that's corresponding to the different input volumes, different slices, depth slices in the input as well. So now we're in the second filter. This is in the first filter. You're using the first filter here. And then you're striding through with a stride length of 2. And then you switch to the second filter. And again, you're striding with a stride length of 2 through the input slice using the second filter. So pretty cool. You can take a look, the link as well. And right, so let's go back to sharing. Okay, so let's start with the in-class exercise. Pretty important to understand what's happening with CNN layer versus a FC layer. So take a minute or two to read through the question and come up with your answer. Like we were discussing, it's between 1.5 million and 1.5 billion, right? So the way to think about it is this is your input block, but since it's FC, you can just think of it as a vector. Okay, so what's the input block size? It's 100 by 100 by 3. Do you agree? And then this is the output block. Just it's kind of similar, 100 by 100 by 5. So I'm making 9800 just to approximate. So since it's FC, what it means is every neuron here is connected to every single neuron here. That's essentially what FC is. Doesn't matter you think of it as a block or it's a vector, you're essentially connecting every single thing to every single thing here. So what does this tell us about the number of parameters? You take every neuron here and multiply by this. Okay, so that means we need to multiply this dimension with this dimension, right? So that gives you 1.5 billion. So switching from a Conv layer to a FC layer is super expensive. You went from 135 parameters to 1.5 billion parameters. So doing neural networks in a naive way can just give you, crazy number of parameters to optimize for. So luckily we don't need so many parameters. It's not like we're losing out on something. Convolutions work great. They're doing the job for us. As far as images are concerned, convolutions work great because images have adjacent pixel values don't change so much. So convolution is able to capture information by just sliding through. If you had to capture information from different parts of the image, then convolution becomes tricky because you're only sliding locally. You're not like looking at different parts of the image. But for most images, you can just like slide and understand what's happening in different areas and then put that information together. So that's where convolution makes it easier for us to extract information and with fewer parameters, just 135 parameters. Where is 135 and where is 1.5 billion? That's crazy gap, right? Okay, great. So this is clear, right? Any questions on this? How we did this? All good? Okay. So we covered convolution, and it's a little bit of detail involved, but I think if you go through it again, you'll see that it's very intuitive what's happening with the convolutions. The second kind of operation that happens in a CNN is the pooling. And we spoke about max pooling specifically. So the idea of pooling is take an input block and then pool to convert it to an output block. So in this particular case, if you want to visualize, you take a particular slice here. So let's say that's a 224 by 224 slice, depth slice. Maybe this is at a depth of let's say 10. So I take the 10th depth slice from this input block, and it looks like this. You can visualize it. It's an image because you start with an image, so you'll get something that's visual. It captures some features, so you can visualize it. And then you downsample, and then you get something that looks like this, right? So 224 by 224, I downsample, I get 112 by 112. And in this case, it's a downsampling by 2. So in each dimension, I'm downsampling by 2. So as an illustration, let's say you had a depth slice that looked like this. So this is a 4 by 4 block, 4 by 4 matrix. It's a depth slice, so it's a matrix. And I do a max spool with 2 by 2 filter and a stride of 2. So what does that mean? It's 2 by 2, so f is 2. Okay, so I start here. Doesn't make sense. F is 2, so I start here. It's 2 by 2. And then I stride by 2. So because I stride by 2, my next 2 by 2 is here. And then my next one is going to be here. The next one is here. And then I'm done because I'm striding by 2. So that gives me 6, 8, 3, 4 because I'm doing a max here. So 6 is the max here, 8 is the max here, 3 is the max here, and 4 is the max here. So that's max pooling. If you did average, you would have to average. That would be a dot product. So max pooling, if you notice, is not doing a dot product. It is taking the max. So it's a different operation, right? So that's something new. In all of what we've seen so far in neural networks, we've been doing dot products. But with max pooling, you're taking a max operation, which you cannot represent through a dot product, right? How do you represent max through a dot product? You cannot, right? Because it's a max value in a vector. So that's what you get here with max pooling. So you see now from 4 by 4, you're going to 2 by 2. Okay, so that's a pooling operation. So why do we do pooling? Pooling reduces the size of layers in CNN and hence reduce the number of parameters. So even though we saw there's only 135 parameters when going from one layer to the other using a convolution, you might have many such layers. And so you may want to reduce parameters. If that's the case, you can use pooling and it reduces the number of parameters. Typical pooling is F equals to S equals to, so we spoke about this. And this is non-overlapping pooling. You can do overlapping pooling as well, but it's less frequently used. Let's say S equals 1, F equals 2, then it's overlapping because your pools, you're still doing max pooling, but it's overlapping information. So when you do non-overlapping, you're downsampling by some factor. So the difference between pooling and the con operation that we had is in pooling, depth doesn't change from input to output layer. So whatever is the depth in the input layer is the same in the output layer. Why? Because you're pooling across every depth slice. So let's say your input had depth of 5. You're going to take each of those depth slices and pool and then put it together. So you're going to get an output block that has the same depth as the input block, except you've pooled it. So the width and the height are going to reduce, but the depth is going to be the same. But in a convolution operation, the depth entirely depends on the number of convolution filters you have. So you are using the depth information when doing convolution, but you're not using the depth information when doing max pooling because you're max pooling across a depth slice. For any given depth slice, you max pool, and then you max pool for every single depth slice. So this is kind of the little bit of a mechanical difference between the convolution operation and the pooling operation. So pooling doesn't change the depth size. Whatever is your depth in the input block, you have the same depth in the output block. Okay. And we spoke about this, pooling can be max or average. So instead of doing a max here, I can take a dot product. If I take a dot product, that would be called average pooling. So maybe I have you kind of divide the value as well by the total number. So then that would be average pooling. So people have experimented with average pooling and they've found that max pooling works best for learning from images. So use max pooling. Okay, let's look at another in-class exercise to understand max pooling better. Okay, so hopefully we got a chance to work on this. Yeah, so you reduce it by about 90%, right? So even using such a small, receptive field size of just 3, so you're just using a 3 by 3 field size for max pooling, and of course using a stride length of 3, this does matter. So what happens is you are going to reduce, your output is going to be 1 by 9 of the input size, right? Roughly. So that's 1 minus 1 by 9 times 100, reduction, that's roughly 90%. That makes sense, right? So using a receptive field size of 3 and a stride length of 3, you can reduce the percentage of neurons by 90%. So if you have any concerns on overfitting, you can just use a large. So for this reason, people don't use a big F or a big stride length, because it drastically reduces the number of parameters when you do max pooling. So typically people use F equals 2, stride length equals 2. So even there, you reduce the percentage, is reduction is 75%. So with pooling, you do lose information. So here's a real world example of convolution neural nets using all the different pieces that we spoke about earlier. So this is the input. So as you can see, the input has some dimension. Well, the dimension is 224 by 224 by 3. So the depth is 3, which is RGB. Then you have so wherever it's not mentioned, it's a conv layer. So you have a conv layer with S equals 4. I think padding is 0. And K is, oh, actually here in this case, K is 96. So you have, okay, there's some structural difference here. Is you'd have two sets of, output blocks, one on the top, one on the bottom. The reason for that is they do GPU computations on the top and the bottom layer. So they're able to speed up the computation when traversing through the network. So that can help with inference. So there's a structural reason to have this kind of a thing, but essentially your K is 96 because you have 48 here and 48 here. So you can put them together, it's 96. 96 different convolution kernels. What else? F is what? What is F here? Anyone? In the first layer, what is F? 11, yeah. In the second layer, it's 5. You can see the F keeps changing from one layer to the third layer, it's 3. So the field size can change from one layer to the other. What else? Okay, so that's conv layer, and then they have max pooling. Then again, they do max pooling again. Then they have a conv layer, max pooling, and then this is fully connected. And then this is the number of classes. So they have 1,000 classes. So this ImageNet computation, you have to predict an image from 1,000 different classes. So we were looking at like 3 classes or 10 classes. Now imagine 1,000 different classes, and you have to do well on all these classes. Then you need such a sophisticated neural network to be able to do the classification. So the output is obviously always the number of classes, and it's going to be a probability distribution over classes. And this is where, at this point, you've kind of learned a representation that's ready for classification. And this is your classification part. You have fully connected layers. So you see this says dense. So dense is fully connected. Every neuron is connected to every other neuron. So that's going to be a lot of parameters. As we saw, as soon as you have dense, the number of parameters goes up. But thankfully, you've already reduced the size here. And these layers are also not super high, but you still have like 2,000 parameters here. So these convolution layers are not actually taking up a lot of parameters. But just 1 or 2 dense layers, you get a lot of parameters. Like here, it's roughly 2 million parameters going from here to here, right? Or whatever, 4 million parameters. So your dense layers are contributing to the most number of parameters in this CNN. Okay. So this whole thing is now called an architecture. So it's a CNN architecture that was used in the ImageNet competition in 2012 to win the ImageNet competition there. So then there's other kinds of architectures. So essentially they'll all have a conv layer, a max pool layer, but how do they get built up, put together? That can be different. So we'll look at a few of these architectures in the next lecture, some of the popular ones that have worked in different cases, different problem spaces. We'll look at that and understand why did they use that. So that'll be for the next lecture. So like we said, the cool thing about convolutional neural networks is you can actually visualize the intermediate layers. So this image is the depth activations or the depth images, 96 of them, right? So 48 coming from the top and 48 coming from the bottom, right? So there's 48 here, 48 here. And each of this is a depth slice. So take each of that slice, and I think it's 55. So if you look at this here, it's 55 by 55 by 48. Okay. So we started with a 224 by 224 by 3. This is a color image. So your image was a color image, 224 by 224 pixels, and 3 for RGB. And each of these is 55 by 55. It's grayscale or whatever. They have a depth as well. Interesting, because here we see color here. That is very interesting. Okay, at least these ones are grayscale. Let's come color here. Okay, let's say it's 55 by 3. You factor in the 3 as well. So you can see that they are doing different things. So if you want to understand what's happening here, it's detecting different things. Like this is detecting some edges in this direction, or horizontal edges, vertical edges. So it's not super intuitive what's going on. Like this is detecting a checkered pattern. So it's saying, hey, this pattern exists in the image. These are detecting some other kinds of hues. So, I mean, you can visualize it, but in some cases you can understand there is some edge detection going on. And edge detection in different angles, right? All kinds of angles. The edges are being detected here. But in other cases, you may not be able to say what is going on, but you can still visualize it. So these are the 96 different depth slices from the first layer after convolution on the input image. This is what it looks like. So you can actually visualize it for every single layer if you want to take a look and interpret it. Okay, so, right. So that's a cool thing. You can visualize and see what's happening. All right, so let's do one more in-class exercise to understand max pooling operation and max pooling dimensions. To look at this. Yeah, this is a very interesting question because it really helps you understand what's happening in every single operation. So clearly, FC and Conv Layer have parameters and hyperparameters. We agree on that, right? So it's not option 2. If you look at ReLU, what is ReLU doing? It's just taking your neurons from the previous layer and then asking the question. If you are negative, I'm going to set it to 0. If you're positive, I'm going to just pass you through. So there is nothing, there's no hyperparameter, there's no parameter. So ReLU is definitely a layer that has no hyperparameters. So it doesn't have parameters, it doesn't have hyperparameters. So clearly ReLU has to be part of the second answer, right? So that gives us 3 or 4. The question is, does MaxPool have parameters? No, it doesn't have parameters, right? Because just, what are you doing? You're just like taking a 2 by 2 or whatever, and then pulling and then putting it there. So there's no convolution, like convolution has parameters because you have to decide what the convolution kernel looks like. But maxpool doesn't have parameters. But does it have hyperparameters? Yes, right? Because you have to decide what is the stride length for a max pool. Like, is it stride length of 2, stride length of 3? Is it overlapping, non-overlapping? Is it a 2 by 2 block or a 3 by 3 block? That is something you decide as a hyperparameter. So even though max pool doesn't have parameters, it does have hyperparameters. So that leaves us only with ReLU. So on the one extreme, you have FC and Conv Layer have both parameters and hyperparameters associated with it. On the other extreme, ReLU doesn't do anything. I mean, ReLU doesn't have any hyperparameters or parameters. So it's option 3. Okay, so maybe it will help to visualize this. So we can do it as layer parameters. Okay, so we have FC has parameters and hyperparameters. That makes sense. FC is your standard neural network. So you have to decide what's the size of the output, what's the number of parameters and all of that. So you have both. Conv Layer has parameters because that's your convolution. Convolution has some parameters. Every single cell in the convolution kernel is a parameter. It also has hyperparameters because how many convolutions are you using? What is the size of the convolution? We spoke about that. What is the stride length? Stride length is a parameter. Padding size. So all of those are parameters, hyperparameters. Then we have pooling. So pooling doesn't have parameters, like we spoke about. Hyperparameters, yes. And then we have ReLU, doesn't have parameters or hyperparameters. Okay. And we spoke about this as well, that in your CNN, your FC is contributing to the most number of parameters. So if you think, oh, why is it taking so much time to train? It's probably the FC layer, which is having a lot of parameters. Or why am I overfitting? Again, go back to your FC layer. So, we know tricks for overfitting here: use dropouts, do early stopping, use regularization, and things like that. So those things still apply for FC layer. Conv layer, as we saw, it doesn't get us a lot of parameters, but you may still have to decide how many conv layers you want to have. So how do people do this in practice? Like, if we go back to this, the winning architecture in this competition 2012, they had about, I don't know, 1, 2, 3, 4, 5, 6 layers. And these days people have 15, 20 layers as well. How do people decide if 6 is good or 20 is good? Well, you can actually experiment with it. You can use your validation data set and see where are you not having improvement. So you start improving as you start adding 1 layer, 2 layer, 3 layer, but the improvement starts to taper. So let's say number of layers, and let's say this is some metric. Maybe you have score or something that you care about. It might kind of go like this. So in the beginning, it makes sense to add more layers. But as you keep progressing, this is like what we call diminishing returns. So as you keep adding more layers, the incremental benefit of adding a new layer starts diminishing. So that's diminishing returns. Or we also call this a submodular function. So you stop having as much, but you do want to add, like, let's say you're using only 1 layer. Okay, that's too small for a CNN because look, you can actually improve on your F score by just adding a couple of more layers. But people start adding more layers, like you're already at 10 layers, you add 15, maybe you'll have a small bump, right? From here to here, that's a small bump. But then from here to here, it's pretty much flat. So after a while, you don't see improvement. So there's no point in adding like 30 layers or 40 layers. It's only going to increase your training time and complexity of your network, it's not really going to contribute. So that's how people kind of experiment and then say, oh, I think for this kind of data set, I think 15 is good, because you'll see this kind of a graph. So this graph is key to understanding how many layers to use. So a lot of CNN is also experimentation. You experiment, you try, and you see. Okay. All right. So we are towards the end of today's lecture. We'll just summarize a couple of more things. So CNN versus NN. The fundamental unit in CNN is a block. The fundamental unit in NN is a vector of neurons. NN only has feed-forward connections, mostly from one vector of neurons to another. CNN has three different types of connections: FC, conv, and pooling. NN has full connectivity. CNN has local connectivity. So we saw locally you're connected. And the parameters in CNN, so in NN, because it's fully connected, you get a huge parameter space. In CNN, you can also say there is shared parameters. So what is shared? Well, the convolution kernel is shared. That's the shared parameter, because you're sliding it, but as you slide, you're not changing the convolution. You still fix the convolution, right? I mean, that's a definition of a convolution, but sometimes you can actually change it as well. So the sharing of parameters is implicit. It's understood because it's a convolution. Yeah. So feed-forward neural network parameter space would be prohibitively large for images. You simply, like, you're going to try neural networks on images for this mini project, right? Don't stress too much over it, but give it a shot, because it's not supposed to be the best architecture. So don't be surprised if you don't get good results. But definitely try it, because it's part of the mini project, but also you get exposure. But the parameter space is prohibitively large. So that makes it hard to train as well. It takes a long time in training. So when you do the mini project, always start small, and then start increasing the number of neurons or number of layers and things like that. So you get your basics right, and then you can fine tune it. Conv nets have shared parameter space and keep the parameter space manageable. So yeah, that's true. Okay, so next lecture, we'll look at some popular convolutional neural net architectures. So there's like AlexNet, and then there's many other nets that you will see. And we'll discuss what these architectures look like, where are they used, why are they useful, and what's the intuition behind them. The intuition is the key thing. You get intuition by reading articles, understanding them, but also by implementing them yourself. When you implement it, then you see what's happening and what it looks like. Okay, so I'll stop here for any questions, and we'll meet again, I guess, tomorrow. Actually, I'll confirm on tomorrow. Hopefully we can meet tomorrow, but yeah, we'll just confirm that on the Discord channel. Okay, I'll stop the recording.